Okay, so first of all, thank you very much to Michael Sachs for organising this session. So today I'm going to be talking about modelling complex disease trajectories using multi-state survival models, estimation, prediction, and software. So the plan for my talk is to give a brief and pretty broad overview of multi-state survival analysis. I will concentrate on parametric approaches and more specifically flexible parametric approaches. So I'm going to talk about using restricted cubic splines to model baseline hazard functions, time-dependent effects, things like that. All the way through my talk, I'm going to show example data code using my Merlin package and the multi-state package that Paul Lambert and I have developed over the past few years. And I'll also talk about some new work. Okay, so as I'm sure many of you know, in survival analysis, we often concentrate on a single time to event of interest, so an initial starting state and a single finishing state. Now, of course, in practice, there's many clinical examples of where a patient may experience lots of different intermediate events, such as in cancer and cardiovascular disease, where patients may experience recurrences, comorbidities, all sorts of intermediate events which may impact future risk of further events. So, of course, this can create pretty complex disease pathways. So this is an example I was involved in a few years ago. We had a cohort of patients diagnosed with stable coronary artery disease, and they were at risk of multiple events, such as MIs, a couple of different types of strokes. They could, of course, die from their cardiovascular disease, or they could die from a non-CVD related cause as well. And the important thing to note here is that each of the arrows, each of the transitions between any two states, of course, represents a transition rate, transition intensity function, which of course we may be interested in modeling. So each transition represents between any two states can essentially be thought of as a survival model. It's governed by a transition rate. And of course, we want to investigate covariate effects for each of these specific transitions between any two states. Of course, what if where I've been impacts where I'm going? So the fact that I've had previous MIs, previous strokes, does that impact my future risk of death? And of course, with the drive towards personalized medicine, hugely expanding the availability of register-based data sources, including improved linkaging between registers, there are huge opportunities to gain a much greater understanding of disease processes and, of course, how they change over time. So the example I'm going to use today comes from is a breast cancer example. So I've got just under 3,000 patients with primary breast cancer, where we've got information on the time to relapse and the time to death. Now, all patients begin in this initial post-surgery state, which is defined as the time of primary surgery, and can then move on to a relapse state or a death state, and of course they could die following relapse. So this is my classic illness-death model. Patients start in my state 1 post-surgery, could have a relapse, could die directly, or they could have a relapse and then die, going from state 2 to state 3. So we have transient states, states we could both enter and leave, and absorbing states, states that once we enter, we can no longer leave. So covariates of interest, in the data set we've got a few available to us. Age at primary surgery, tumour size, classified into 3 levels, small, medium and large, let's say. Number of positive nodes, progesterone level, and whether patients were on hormonal therapy at baseline. So, multi-state models. I'm going to look at general multi-state models, and then in particular concentrate on Markov models, and then relax that later on in my talk. So if we consider a random process, capital Y of t, which takes the values in a finite state space, defining a set of states, and we define the history of the process up until time s to be capital H sub s. We've got the collection of states visited across follow-up time. Now the transition probability can then be defined as probability of being in state B at time t, given that you were in state A at time s, and conditional on the past trajectory up until just before time s. Now quite often we make the Markov assumption. Now a Markov multi-state model makes the following simplification. It implies that my transition probability is only dependent on the present. So we lose that conditional dependence on the past trajectory. We're only conditioning on being in state A at time s. Okay, so it's implying that the future is only dependent on the present. Now this simplifies things a lot for us later, but of course it's an assumption. Now, what if time spent in previous states? What if previous disease history, states that we visited, anything to do with this previous history, what if that impacts it? Does that violation matter? Okay, so how do we bring together and classify and model our multi-state model? Well, we can do this in terms of our transition hazard functions. So I can define H sub k, so it's the hazard function for the kth transition, which represents the instantaneous risk of moving from state A sub k to state B sub k. Now our collection of transition intensities, transition hazards, governs the multi-state model. So we have a set of transitions, we have a set of transition hazard functions, put them together, and we completely specify our multi-state model. So this really is simply a collection of arguably standard survival models. Now there's lots of challenges in terms of estimating transition probabilities, arguably what we're most interested in, both within non-semi-parametric and parametric frameworks, which I'm not really going to go into today. But essentially a multi-state model can be specified by a combination of transition-specific survival models. Now, just to flag up, I am assuming exactly observed event times and no sharing between transitions. Now, the most convenient way to do this, to tackle multi-state models, is through what's known as a stacked data notation, where each patient has a row of data for each transition that they are at risk for, using start and stop notation, standard delayed entry setup. Excuse me. So, apologies to our users, but I'm going to show quite a few example bits of Stata code. Hopefully, regardless of what you use, this will help illustrate what we're doing. So I'm simply loading my breast cancer dataset. It comes in wide format, so I've got a single row per patient. We have their time of relapse, or relapse-free survival time, and associated event indicator. I've got my overall survival time and my associated overall survival indicator as well. So the first patient didn't have a relapse, didn't die, so they were censored for both competing risks, relapse or death, after just under 60 months. Second patient had a relapse at 16.5 months and subsequently died 24 months post primary surgery as well. And we've got our baseline covariates as well. I'm just showing you age, for example. So how do we turn that into wide format? Well, we can use the msset command, which is part of the multi-state package in Stata. We apply msset. I specify my state indicator variables and associated event time variables. Now I haven't specified a transition matrix, so msset assumes the default, which is the illness-death model. I've also passed my covariate age, and it will expand it into transition-specific versions of itself for use in modeling later. Again, I didn't specify a transition matrix, so it's assumed the default. We can actually extract it from the return list of the command. It's stored in our trans matrix. So here we go. This is the model. This is the transition matrix which governs the multi-state model. Patient start in my start state. Transition number 1, moving on to relapse. Transition number 2 is going from start state, primary surgery, to death. And transition number 3 is going from relapse to death. Let's have a look at the data. It's now in long format. It's created some internal variables, these underscore variables, defining the starting state, from state, the finishing state, my to state, and the associated times of entry and times of exit and event indicator. So the first patient started in a state 1, could go to state 2, or could go to state 3, so competing risks. They start at time 0, at risk of relapse and at risk of death up until 59 months. In this case, they were censored for both outcomes, for both competing risks. Now, these observations contribute to transition number 1 model and transition number 2 model. Second patient, again, start in state 1, at time 0, could go to 2, could go to 3. They had a relapse, so at 16.5 months, they were censored for death, but they were censored for that direct transition to death, but they experienced a relapse. So we get a new observation. They start in state 2 now, at the time of relapse, and they're now at risk of death following relapse, in which case they did, in this case, after 24 months, they subsequently died. So this observation, of course, contributes to transition number 3. Okay, so now our data is restructured. We can essentially apply any standard survival model we may wish. Now, the stack data set format is useful for imposing things like proportional baselines across transitions. So we could fit a single model to our stacked data set. We could stratify our by transition number to allow for stratified baseline hazards. We could allow shared or separate covariate effects across transitions, and of course we could allow for simple or complex time-dependent effects. And of course, each transition model should be as simple or as complex as required. Now, in this talk, I'm going to concentrate on using my merlin command, which is a very, very general command developed for mixed effects regression for linear, nonlinear, and user-defined custom models. Primarily developed in Stata. There is an R version now up on Crown. It's a bit behind the Stata version, but please do have a look. Now, Merlin can fit some very simple models. So this is just how we apply a viable survival model to a standard data set. My survival, event, censoring time, adjusting for treatment, adjusting for age. Specify the distribution. It's a viable survival proportional hazards model. So I have to tell it my event indicator as well. Merlin can also fit very, very complex models. So this is a 4-outcome joint multivariate longitudinal model and competing risks. Okay, so there's lots going on there. I won't go into much detail. There's lots of examples on my website. But essentially I'm modeling 2 normally distributed Gaussian biomarkers, let's say systolic and diastolic blood pressure, flexible functions of time, fractional polynomials there, restricted cubic splines there, random intercepts for both of those models. And I'm modeling competing causes of death. The first one with a Roast and Palmer spline-based survival model, the second with a Weibull, and I'm adjusting for treatment and age in each of the cause-specific models, and I'm linking the expected value of the biomarker in the linear predictor of my survival model for cause 1, same thing for cause 2. I'm linking its rate of change, and I'm linking the integral of the expected value, so like a cumulative exposure in the model for cause 2. Again, lots going on. Merlin is very, very general and very, very flexible, especially in the sort of joint modeling literature. But going back to standard survival analysis, in the latest version of Merlin, there's now this stmerlin command, which is essentially a wrapper function, which makes our lives a little bit easier in fitting survival models. So standard syntax in Stata, so I'm going back to my stack data set. I've got my stop variable, which had my survival times for each transition. Enter time, so in other words, time of entry into each state, so we're allowing for left truncation. And my associated event indicator as well. So in Stata, we must declare our survival type data using stset, and then we can use every sort of different ST modeling command, parametric Cox models, and now stmerlin to fit the equivalent Weibull model, as I showed before. So if I restrict my sample to just those observations contributing to transition number 1, I can fit a simple model, adjusting for hormone and age. Okay. So I'm going to jump straight into essentially 3 final models for my 3 transition models. The point I want to get across is that these models can be as simple or as complex as required. They could be as similar or as different as required as well. So this is my model for transition number 1, restricting my sample, adjusting for all of my covariates of interest. I'm assuming a Roast and Palmer model for the baseline hazard function, so I'm using 3 degrees of freedom modeling on the log cumulative hazard scale. I'm allowing for time-dependent effects in the effects of tumor size, both medium and large, with the smallest as my reference, and progesterone level as well. Each of those forming an interaction with a single degree of freedom for the spline of log time, which is the default in this case. Okay, so lots of flexibility to be able to model, and this is just for transition number 1. We do the same thing for transition number 2. I've just got a Weibull model in this case, so again, there's no restriction that the model that you choose, the family of models that you choose, has to be the same for each of the 3 transitions, because we can fit completely separate survival models for each transition. Finally, transition number 3. Excuse me. Again, I'm going back to a Royston-Palmer model, 3 degrees of freedom. Only evidence of non-proportionality in progesterone level in this case. And again, modeled with an interaction with log time. Now, what I haven't mentioned is that after each of these model fits, I'm storing the model objects. So I've got model 3, model 2, model 1, okay, for transition number 1, 2, and 3. I've stored my results, okay? Now, calculating transition probabilities, arguably the thing we're most interested in. Probability of being in state B at time t, given you're in state A at time s. Our transition rates completely specify the multi-state model, so how do we then calculate our transition probabilities? There's lots of different approaches. Again, I'm going to go whiz through these. Exponential distribution, extremely convenient in terms of calculation, including its piecewise extension. Numerical integration can be used for more complex models, pretty appealing, but difficult to generalize beyond an illness death setting. Some really nice work by Andrew Titman looking at ODEs, extremely appealing, but difficult to generalize beyond sort of Markov setting. And finally, there's a simulation approach, which I tend to favor. Not always. It can be computation intensive, but it's extremely general in the tools that it gives us to calculate such predictions. So, simulation. Given our estimated transition hazard functions, we simply simulate a large n number of patients through our transition matrix using the transition rates, the estimated transition hazard functions. Really simple. At specified time points, we simply count how many observations, how many of those n simulated observations are in each state, and divide by the total to get our transition probabilities. To quantify uncertainty, we simply do a parametric bootstrap around that simulation. Okay, with mean vector, the estimated coefficients from the intensity models, and associated variance covariance matrix. And we simply repeat this a large m number of times. Now, importantly, regardless of the complexity of the model, we can still simulate survival times. There's work that I did during my PhD with Paul Lambert, producing this sort of general simulation algorithm to generate survival times from essentially any simple or complex survival model, which we utilize here. Okay, so getting to the core command of the multi-state package is this predictms function, which calculates our prediction. So given my estimated models, I'm passing my model objects M1, M2, M3, which get tallied up with my transition matrix. We saw the matrix, it had transition number 1, number 2, number 3. They match up simply with our models. I request transition probabilities, and I'm making a conditional prediction. So I'm going to set age to be equal to 55. All other covariates are set to be 0. And this is what I get. It produces transition probabilities at specified time points, and I can simply plot them to produce these nice and easily interpreted transition probabilities. So probability of being in alive and alive and relapse free, alive and having had a relapse, and dead. Okay, so we get these much more useful probabilities of being in each state as a function of time, even though my underlying model has splines everywhere, time-dependent effects, doesn't matter. A really simple prediction call to get these transition probabilities. Okay. If we want uncertainty, I've moved things around. All I've added is my CI option, and off it goes and does that parametric bootstrap. And I get my uncertainty on my transition probability, so probability of being in each particular state. We can do multiple at statements in a single call, so I could specify at 1, at 2, at 3 for varying levels of tumor size at baseline. So these three correspond to this one, so nodes of 10. So we can see the increasing risk of death as tumor size increases. Okay, so nice to be able to quantify the impact of covariate changes, but not always easy when contrasting these measures. But they're useful. So I think it's going to allow us to answer questions such as how does treatment change the probability of being in each particular state. Just looked at this. How does tumor size at diagnosis influence these probabilities? How about using differences and ratios to contrast these things? Rather than trying to visually compare across two graphs, we could quantify the differences. Really simple. I add my difference option, and it does the difference between all my ats compared to a reference one. By default, it's at 1. I've changed it to at 2 in this case. I'm also going to get confidence intervals for free, not only on my transition probabilities, but also on my differences. So this is the probability of being in my post-surgery state, so still alive and relapse-free. Higher probability of being in that state if we have a smaller tumor size compared to if we had the medium tumor size. Okay, and we can quantify that on the difference in the transition probabilities for any particular state. Finally, in terms of extended predictions, standard predictions if you like, we've got length of stay. Really useful measure, which essentially defines the amount of time spent in any particular state. It's simply the multi-state equivalent of restricted mean survival time. So we're integrating those transition probabilities across time. Easy to get. Thanks to the simulation algorithm, it's really simple to extract these predictions. I add my LOS option, and I get the length of stay spent in each state. So after 10 years, or out of potential 10 years, on average we spend about 7.5 years alive and relapse-free, 1.5 years alive but having experienced a relapse, and of course time lost due to death, we lose about 1.5 years. Okay, confidence intervals, differences, all of these things apply now not only to transition probabilities but also across length of stay. So we get these as well. We get my differences in length of stay across different covariate patterns. So here again, I'm comparing across tumor size, the impact of tumor size. Okay. Also added the ratio, if you prefer ratios than differences. Okay, some further topics. I mentioned briefly the Markov assumption that we're making, that I have been making in these models. It should always be asked, of course, is it valid? It's an assumption. Does it matter? So there's some nice work looking at robustness, validity of the Arlen-Johansson, the non-parametric Arlen-Johansson estimator in the non-Markov setting, showing it's essentially valid for general non-Markov models. Now, of course, if we're interested in modeling, and in particular in observational data, we're often interested in modeling rates, where there can be, of course, more than one timescale of interest. This Markov assumption starts to break down. We could be interested in modeling time since diagnosis, attained age, calendar time, time since intermediate events. All of these things can be clinically interesting and useful to quantify disease processes over time. Now, modeling such a multiple timescale survival model is not a simple thing. Now, in our breast cancer example, ideally we could be interested in time since primary surgery. That's our main timescale. But in that transition from relapse to death, we've also got time since relapse, or indeed time of relapse. We can now do this with my merlin command. So again, I'm not going to go into too much detail. My main underlying timescale, delayed entry, I can adjust for time of relapse and also model time since relapse with an offset. So take away the time of entry from my survival time, which recovers my time since relapse. It's a very general command to fit such multiple timescale models. Fit the model, it's the same one as before, store it again, pass it to predictms. Okay, so predictms works really nicely with multiple timescale survival models. Okay. Last little extension. So far I've been assuming exactly observed event times. Now, this allows us to fit either separate or stacked models because the likelihood factorizes, Now, what happens when we have interval-censored observations? So interval censoring means essentially means that we know an event occurred between a particular time interval, but not exactly when. So this is really common in the setting of ophthalmology, dentistry, where patients have regularly scheduled visits, but of course conditions are only picked up at such visits. Now, interval censoring in a standard survival analysis setting is available within a couple of commands in Stata, st-intreg, the stpm, and the merlin package in Stata, where we just need to specify this L interval option, which defines the left boundary of our interval, and our outcome now specifies the right. So we've got interval censoring as well. Not so simple in the competing risk setting, where we know an event occurred and which event it was, but we don't know when. So until we have that event, of course, we're at risk of all our competing events. So the event can occur across a range of time points, which means we can't fit separate models. We must maximize a joint likelihood. So across my interval, we must integrate and evaluate, essentially evaluate the potential competing risks that we have up until our time points of interest. So this is all implemented again in the merlin command. Because it's set up for modeling multiple outcomes, I can have cause 1 model, cause 2 model, specify my intervals, and now add the new option, transition matrix, which tells Merlin that I'm fitting a competing risk model. So it uses the appropriate likelihood contribution for that setting. Once we've fitted the model, we predict as normal. Predict my cumulative incidence function, my transition probabilities, for the competing risks setting, for the first outcome, for the first cause, for the second cause. Really, really simple. There's also RMST to get restricted mean survival time, etc., etc. Unsurprisingly, general multi-state setting is a bit more challenging, which I want to talk more about today. Okay, to finish up, I've whizzed through quite a bit of simple and complex modeling. Balancing those two things, complexity and plausibility, is of course challenging, especially in the multi-state setting where we have lots and lots of different models that all piece together to formulate an overall multi-state model. So of course, as standard, we should always think first, model second, balancing that complexity, whether it's needed. But of course, what I really focused on today is trying to report complex models in an approachable way, which is, of course, pretty challenging, especially given the growing interest in machine learning, AI methods, making this, I think, making that aspect even more crucial. So providing easily interpretable predictions, regardless of the model complexity, is a really important thing. Just some future work that I didn't really have time to mention. Regression standardization. So there is a standardize option of predictms, which allows us to obtain marginal predictions on any of the things I've shown today. Again, I mentioned with Merlin, Merlin can fit random effects models, multi-level models, joint longitudinal survival models. All these things will start to feed into the multi-state predictms package as well. So for allowing for frailties, for example. Lots more details and examples on my website in terms of Merlin and multi-state. And just to finish with some acknowledgement, so Paul and I have worked closely on this multi-state stuff for many years now. And Caroline Weibel here at KI has also been leading lots of this work on the multiple timescales as well. And some references. Okay, thank you.